Hi everyone, and welcome to another video of heat transfer. So for this video, we'll discuss the introductory concepts of convection before we dive in into the problem-solving parts of convection. So it will be important to have a basic understanding of the terminologies before we really get into actions. No? So the general outline is as follows. We will discuss the uh, how convection works and what are the classification of fluid flows. There's a brief comparison of the different flow regimes and what is the velocity boundary layer, the thermal boundary layer, and what are the governing equations in fluid mechanics and heat transfer in general. Okay, so let's begin with the convection heat transfer. So nothing really changed here. We've discussed this in the first chapter, the first topics, that the convection heat transfer is just this equation. No? So you have this H as your heat convection transfer coefficient, and then you have the area of the surface that is frequently just lateral surface area of your surface of your body, and then you have the temperature of the surface and the temperature of the fluid or the free stream temperature. So you have here a flow of air going at 20 degrees Celsius. So that is the free stream temperature. No? And basically what you have to know here is that it might be deceivingly simple, but the real hard part here is how to solve for each. No? So you can basically measure the area, you can measure the temperature of the surface and the free stream temperature, but finding the coefficient appropriate for the scenario will be dependent upon a variety of parameters or variables. So we know for a matter of fact, using experiments that this depends upon this fluid properties and parameters, and also the physical roughness of the surface, including the type of fluid flow. So the dynamic viscosity mu, which is also in Pascal seconds. So in some cases, you might see this as um, kilogram per meter second. No, it's basically the same. And then you have thermal conductivity. We already know this. Fluid density, and then the fluid velocity. No? So the convection heat transfer actually highly depends upon the fluid velocity. So if the velocity is high, the convection heat transfer will be high. No? If you can imagine, if your electric fan is turned on at a high, no, at its high setting, it will feel much more colder. No, so we've discussed this before in the first topic that our sensory information um, that our sensory information regarding temperature is a little bit different that in our intuition that it is not really the temperature that we are experiencing, but rather than the the heat transfer that we are experiencing. So you feel cool because there is convection heat transfer due to your electric fan for this example. No? So without the electric fan, you will only feel natural convection, or in a very simple example, it could be just conduction and radiation. But you know that if the electric fan is pretty high, no, in its setting, you will feel a lot cooler, no? But reality is the temperature of the air is just constant, no? If you can imagine, it's just 25, but it's moving towards you. That is why it feels colder. So convection is the same thing, no? So the fluid velocity highly affects this H, which increases the convection, no? Which increases the heat loss, no? That you feel. No? So another thing that it depends on is the roughness, or the literal roughness of the surface, and also the type of fluid flow. So I hope this will be clarified in fluid mechanics, what is laminar turbulent, but we'll discuss this here as well. So if it is laminar, no, it is very smooth flow, for turbulent, there are eddy currents, no, or vortices, no. There are some chaos in the flow. So now the very basic way to really find this convective heat transfer coefficient is to understand that if for example this surface here in this image has a velocity profile, as you can see. So at this point in the in the fluid of the fluid, the velocity is quite constant, right? For this example, but as you go closer and closer to the surface, it will go slower. So why does it go slower? Because of friction, no? So and your fluid also has a viscosity, so it also contributes to this drop in velocity. So at the surface, you can assume that the velocity here at this surface, no, based on this image, that this should be zero. No? At this very surface level, the velocity is zero, which is also called the non-slip condition. No? So the non-slip condition. No? So at this non-slip condition, you can see that at this point, at this specific point here, actually this line here, at this specific line here, wherein the velocity is zero, it only experiences conduction. No? So why did I say that? So if your fluid is moving, it is convection. But if it is not moving, it is conduction. That is the very simplest way of analysis between convection and conduction. So convection is still conduction, but the fluid is moving. No? So you can imagine that if this is not moving, no, let's say this is not moving, so it will be purely conduction. No? So air, the heat will go through here or the other way around. No, nothing really happens. No, but if it is moving, so buoyant force might contribute to that motion. But if that is force, no, so if you have an electric fan here, then your air is continuously replaced, no? So instead of conduction, no, a very simple conduction, which is, for example, that is 100 degrees Celsius and this is 40 degrees Celsius, this surface right here. If this is not moving, no, again, if this is not moving, if your fluid is not moving, it will be purely conduction. And what happens, no, we know for a matter of fact in transient conduction that what will happen is it will try to reach an equilibrium state. So for example, the equilibrium state will be 60 degrees Celsius for both, no? For example, so it will only reach 60 degrees Celsius, our surface. But if you can imagine, if it is moving, no, if it is continuously moving, 100 degrees Celsius of air is continuously moving here. So we know that 40 degrees will not be the equilibrium. Instead, it will be also 100 degrees, no? So after a while, the temperature of the surface will be 100 degrees as well. So that is the best analogy I can give you how convection and conduction relates to each other. And again, at this line here, it will be convection. Sorry, conduction only here, no. So if we do a node analysis, no, convection and conduction. So conduction and convection at this point, when y is equal to zero at this axis, no, then basically this is the Fourier's law, no, but the derivative is set as y is equal to zero. So if you simplify that, you can get H if you know the temperature profile. If you know the temperature profile with respect to the height, no, then you can also find the H. So that is another simpler way, no. But we know that this temperature profile is quite hard to find, so that's why we have a much easier way. No, we don't really need to know this at this point. No, not really that much, but it is quite important in the derivation of a lot of the convection processes. Okay, so another important thing about convection is the use of this non-dimensionalized number. So we've already dealt with the Biot number. You can remember in the Fourier number. Now we are introducing a new number called the Nusselt number, which is just the ratio of the convection over the conduction of the fluid. So if you can see here, maybe you realize that this is similar or maybe the same as the Biot number, no? Right? So actually, it is different, no? So for Biot number, just to have a note here, for Biot number, okay, the K in the Biot number is the K of the body, no, or the surface. But for Nusselt number, the Nusselt number, the K here, thermal conductivity here, is the K of the fluid. That is the main difference. So they are different, no? So the Biot number and Nusselt different are different with regards to this thermal conductivity. Okay? So we will need the Nusselt number because usually the relationships on the mathematical models that help us solve for the convection heat transfer needs H. So we will need the Nusselt number, no? We want to solve the Nusselt number using some relations in the other numbers actually, And solving this, let's say we know already the the LC, the characteristic length and the K, then we could solve for the H, the heat convection coefficient. So that will be the common process for solving convection. So for the comparison of different fluid flows, just to give you an idea of what they are, no? So viscosity is just again, no, the property of the fluid that resists flow, no. So basically, if your fluid is a little bit, what do you call this, viscous, um, so an example of viscous fluid is honey, no? So a non-viscous fluid or a less viscous fluid will be water. So comparing these two, you can see that honey is much viscous, no, or much more resistant to flow than the water, no. And usually in fluid mechanics, no, not just in heat transfer, we have different types of or different portions of analysis. No, usually we just imagine this. The simpler way is we have inviscid flow. No, we are assuming that the flow is inviscid or not viscous. No, there is no viscous region. But in real life, there is this portion that it is the viscosity is much more apparent. No, when it is near the surface. So an example of this is this airfoil right here. So you have a fluid and you have this airfoil. And as you can see, this portion here, no, or a little bit of this portion here gets a little bit too compressed, no, compared to the other portion of the fluid. So that is the viscous region, no. So the other part here is not really relevant, no, but it is called the wake, no, and the pattern it generates here is are called the vortices or the eddies, the circular no patterns, which is a remnant of turbulent flow. So we now compare the external versus the internal flow. So remember that if it is external flow, externally, the fluid is external. No? Okay? For internal flow, the fluid is internal. That's the very simple way. No? So we have different flow schemes or flow regimes, and we have different formulas or analysis, no, for solving the particular convection coefficients or convection heat transfer. Okay, now, so we also have compressible and incompressible. So the difference between the two is compressible flow has a varying density. Realistically, density will vary. Buoyant force will also be at play at most of fluid mechanics. But in simpler cases, we assume that the fluid is incompressible, especially if it is water. No? So water is negligibly incompressible. No? So we will just using incompressible. Compressible flow is much more complicated. No, not really that much, but it is much more complicated. No, for analysis. And then for the two types of convection, no, we have the forced convection and we have the natural natural convection. So the flow of the natural will be just due to buoyant force. No? So if you can imagine, if you get something cold from the refrigerator, for example, ice, no, right, ice cubes, or maybe a cold drink, the the smokes that come off, no, it's actually the moisture that tries to condense within the air. It is going down, no. But if it is hot, no, if you have a hot coffee, the smoke will go up. So the buoyant forces, or not Well, the buoyant forces, yes. Uh, because of the difference in densities, these buoyant forces attract this fluid flow. No, so we have two types: the natural and the forced. For the forced, literally forced, no, and we will discuss the forced first because it is actually much simpler than the natural one. And then for steady flow and transient flow, so for steady flow, literally just steady, no. But for transient flow, you have this um it's not developed, no, underdeveloped flow. So you can imagine the comparison of this transient and steady flow is when you initially open um your faucet, no, it will be transient, no, but after a while it will settle down. It will be steady. So that is the difference between steady and transient flow. And usually transient is incorporated with initial, no, initialization. Compare this with unsteady. Sometimes unsteady is used interchangeably with transient, but actually they are not really the same, no. Although they have similarities, usually transient flow is usually used for initial flow. Unsteady is for literally unsteady, no, anywhere in time it could drastically change. No? But anyways, this is just terminologies. We can use them interchangeably in this very simple context. And then we will not discuss really the different, no, types of dimensional flows, but you can imagine it can get much more complicated once we introduce more and more dimensions. So in these cases, we will only consider one, no, quasi one, no. So we will only achieve quasi one dimension, or it is actually two dimensions, but we assume that the velocity or one velocity will only dominate, no. So let's say just right or left only. Okay. So for laminar and turbulent flow, so we have two different flows. So for laminar, you can imagine laminar flow as the flow of honey, no? And turbulent flow might be the flow within the pipes of your home, no? It's turbulent, no? So you can imagine laminar flow to be consistent with low velocities, no? If it is low velocity, it is much more smoother, cleaner flow, and lower viscosity. So if it is honey, no, for example, high, actually it should be high viscosity, no? So low velocity, high viscosity. So if it is high viscous, it will be laminar, no, for most of its range, no. But for less viscous and high velocity fluid, it will experience more turbulent flows, no. So um, for example, water is for most cases will be turbulent, no, more turbulent, no, can introduce more turbulence versus honey. Okay, now with regards to that, no, we can actually measure the the fluid if it is laminar or turbulent based on this Reynolds number. So there comes um a point wherein it is laminar, or sorry, um a limit wherein it is laminar. For example, 0 to 2,300 will be laminar, and then 2,300 onwards will be turbulent. So the Reynolds number describes that difference, no, the laminar versus the turbulent flow. So it is dependent upon this two, no, which is the ratio of the inertial versus the viscous forces. So for the inertial forces, you have this velocity, no, v, the big V here is the velocity, LC is the characteristic length, and divided by the kinematic viscosity. So we might use either this one or this one. So just take note that we have two types of viscosity, the dynamic and the kinematic viscosity. So the difference of the two is just the density, no. So if you divide the density from the dynamic viscosity mu, you will get the kinematic viscosity. Okay, so we'll discuss later which will be the LC, no, depending on the case. Okay, so for the velocity boundary layer, just to discuss a few, there will be some regions where it is laminar, no, and some portions wherein it will be turbulent. No? So frequently, no, if you want to have a highly convective scenario, you want the flow to be turbulent. No, but the problem with turbulent uh, schemes, it is actually harder to predict. No, the equations are much more complicated. It is much more chaotic. No, but with regards to the velocity boundary layer, it increases if it is much more turbulent. No, so for laminar flow, the boundary layer is much smaller, no, or much thinner. So you can imagine the boundary layer as just the layer at which the velocity changes from the zero, no, so the zero velocity to 0.99. So if it reaches 0.99 of its free stream velocity, so the velocity here, no, will be this constant v infinity. So the point at which it is 0.99 will be the velocity boundary layer. And the velocity boundary layer has different regions, actually just laminar and turbulent. The transition region, no, just to discuss this a bit, is just the overlap of turbulent and laminar region. So you can imagine the transition region as partially laminar, partially turbulent, no? But it is actually still turbulent, no? So we consider this transition region still as turbulent because slight turbulence is still turbulence, no? Something like that, no? And then for the region here, we have for the turbulent region only, we have the buffer layer and the viscous layer. Okay. So again, the velocity boundary layer thickness, no, is just the point wherein the free stream velocity is 0.99, no. So let's say the free stream velocity is 100, no. Velocity is 100 meter per second. Then the thickness here is when the velocity is 99 meter per second, no. So the thickness here, for example, will be 1 millimeter. Then that will be the velocity boundary layer. No, that's basically that. No, okay. And then for okay, I won't discuss this much, but you have also the shear stress of the walls and the friction of the walls. And we have here a table of the dynamic viscosity of the different fluids. So this might be the average, no, dynamic viscosity of the fluids here. So we will use tables to get the exact dynamic viscosity because dynamic viscosity actually varies, no, with temperature. So you can imagine, for example, the best example might be oil. So oil will be more viscous if it is colder, no? It gets a little bit clumped together at cooler temperatures. But if it is hotter, it will be less viscous, no? Okay? So it is a function of temperature. So we have a lookup table for determining the exact, no, or at least the approximate viscosity at certain temperatures. Okay, so for the thermal boundary thickness, that will be the thickness, no, of your boundary layer in temperature, wherein the temperature is 0.99 of the free stream temperature. So for example, again, if your free stream temperature is 100 degrees Celsius, so find the point at which it is 0.99, or sorry, 99 degrees Celsius. For example, this point here, that will be the velocity boundary thickness. Okay, so as you can see, it can vary, no? The thickness can vary depending on the position, no, of that or the position of this prism. So it varies throughout this, but it will have this. Still, it will have a limit at which it will be consistent, no, depending on the flow scheme. Okay, so the Prandtl number is just the ratio in between of this two. No, actually, in somewhat way, the Prandtl number is just another dimensionless number, which is about the ratio of the boundary thicknesses. No, so the velocity No, it describes the boundary thickness of the velocity versus the boundary thickness of the temperature. So the relationship of that will be the Prandtl number, which is represented by this, no, or this one. So you have V. This is the kinematic viscosity, just to differentiate this with velocity, and then you have here the dynamic viscosity, specific heat, thermal conductivity. Okay, so that's it for the thermal boundary and the velocity boundary layer. Lastly, we have the governing equation. So for the governing equations, yes, it is quite a lot, no? But we won't be discussing much of this, but just to give you an idea that the basis of a lot of fluid mechanics and heat transfer problems will be based on this differential equations, which are just basically it's just the mass, no, mass balance. You have this force balance, no, and you have this energy balance, no, in the form of differential equations. You can represent the fluid phenomena. So you can imagine the first application of this that you can relate with will be, if you might ask, is how do they simulate, for example, the water, no, water simulations. How do this simulation programs represent also the temperatures of certain scenarios? We can use this equations, no? But this is actually still a very simple equation compared to what can be used, no? Because this is just one dimension flow, no? Actually, this is actually two dimensions since we have two space variables. But frequently we say that this is quasi one dimension because only one velocity is dominant than the other, no? Anyways, this is also called the Navier-Stokes equation, no? These first two equations. The energy equation will be just the heat equation. Okay, so that's it for this video. Thank you guys, and see you for the next one.